Okay, everybody, let's get started.
All right.
Okay. Let's see. Hi, everybody. Thank you all for joining us for another Always Coding Hacky Hour. My name is Liz Oz. I'm the head of marketing here at alwaysAI, and I'm super excited here to be hosting the Hacky Hour for today. Hacky Hour is an event that is designed for our community and to share new product releases, do code demos, and have engaging exercises in an interactive format. So, feel free to utilize the chat window on the side, the right-hand panel, or raise your hand throughout the presentation to ask questions, and we'll be happy to answer them as promptly as we can. This event is really all about you, again, so please feel free to ask questions as needed. If you're joining us for the first time and you're new to alwaysAI, as the little intro mentioned, please make sure that you sign up for a free account by visiting www.alwaysai.co and click the little red button in the upper right that says sign up and create a free account to get started, okay? So we have a very special Hacky Hour in store for you today. We're going to be covering AprilTags, Kalman Tracking, and other significant updates to our middleware. So we'll also be having a special giveaway at the end. So please stick around and pay close attention throughout the presentation because we'll ask you a question at the end. And whoever can answer correctly and fastest will get a special giveaway. So now I'm going to hand it over to the master himself, co-founder and CTO, Steve Grisette, and he's going to kick things off. Steve?
Hi, everybody. And well, it's good to be back in Hacky Hour again. So I just want to talk a little bit about the changes we've done to Hacky Hour. Liz kind of outlined some of them, but what we decided was there was a whole lot of information coming out to the community. We have OpenCV that will run Hacky Hour tomorrow, and there was all kinds of things. So what we decided to do with Hacky Hour is go ahead and when we have an update in one of the elements of the product like Edge IQ, which we'll go through today, or model retraining, we're going to come out with a Hacky Hour. Or if we have something very interesting to share, we'll also hopefully get back out to also doing workshops for companies. As COVID starts to, at least in the United States, starts to tamper down and we fully start to open up, like in California in June, we'll be open to that. So I encourage, if you want to have something for your company or so forth, that you contact our sales team and they can start to work on that. And then we're also hoping next September, as schools start to come back in, that we can get back out there and do some hackathons and do some education that way. So, now that we're starting to emerge from COVID, we're hoping that we can start to utilize these other channels too to train. But we want to make sure that we have interesting content, and that's why we've kind of changed up from weekly now to more of a product type of driven and product change type driven Hacky Hour. So anyway, I just wanted to go through that. With that, Liz, let's go quickly through the agenda, although I think this is going to be a repeat of what you said, but let's jump to the next slide if we can.
Sure, thanks, Steve.
Thanks. Oops, that's the introduction guy.
There we go.
All right. So So everyone knows me as a CTO, but I also am the product manager of Edge IQ. And so I've got the Edge IQ team here. I've got my coworker Steve, who you can see on the screen, and Eric's here, and Tyga, and Lila, and everybody we all come to know from these Hacky Hours are on with me, and that is the Edge IQ team. And so with that, we have a new release that we're coming out to, and it's Edge IQ 1.30. And you can get that simply that we now have a desktop vehicle that hopefully you've installed, and that desktop will download and load up all the features of Edge IQ 1.30. Within that new content, we have a couple new features that are pretty important, and we'll go through those things. But we're going to do Kalman trackers today with Steve, the other Steve, the better Steve. And then Tyga will be introducing AprilTags. And really, if we go look at Kalman trackers, just to take some of it, Kalman trackers is a far more accurate tracker than we currently have in the portfolio. So we're really excited about getting that out. And he'll explain why, Steve, why it's more accurate than what we currently have in Centroid-based tracking and so forth. AprilTags are great to build 3D applications on, specifically around robotics. So what AprilTags do is add more data to a robot. When it's looking out there, it can see a thing. Should I turn left? Should I turn right? What am I looking at? How far away is it? So you can start to add some dimensionality with AprilTags, and Tyga's going to go all through that. So let's go through and review everything that we've got going on from the Edge IQ team in 1.30. So next slide, please, Liz. All right, so we've just talked about it. Of course, the brand new features that we're pretty excited about are AprilTags and Kalman trackers, on that. But then we also had a series of enhancements. So many of you don't know, we've been running really between our ARM devices, our ARM764 and NVIDIA platform, we've been running different versions of OpenCV. And the reason we've been doing that is because of OpenVINO problems with OpenCV. Now, OpenCV has resolved those problems. So what we've done is take some of our open source middleware like OpenCV, and we now have OpenCV 4.51 out there. And then we've upgraded OpenVINO version. And that's really important too, because when you're loading the myriad processors and getting to that new version, is it also updates the firmware, or not really the firmishware, or the piece that goes into the processor and does that. So now that's all updated. As most of you know, we've been running Python 3.6 to death. We've been running for over a period of long time. We haven't upgraded our Python environment. So we're now upgrading to Python 3.7. So we're moving from the 3.6 form to 3.7 now. I think the impact there is you can use more up-to-date third-party libraries and so forth. The bad news is, as you're doing your projects, you have to be aware of that and changes that come within those. So you may have to add, so if you're adding something like Pillow and you're running a Mac, you may have to update some of your JPEG libraries and things like that on the side. But it is change, it is get better. Steve was on the call, the good Steve. He's taken analysis. He looked into YOLO v3 and how we were handling post-processing. So he added some speed ups in the post-processing, which should help your YOLO models execute faster. So that's in the code line now. And if we remember back, the last major release, we added OAK-D camera support in. But we've also updated it. And so the problem there in the OAK-D is we were using a non-blocking system. So what does that mean? So when you got something back from the camera, data back from the camera sensor, what you got was a none, and you had to handle the none case. And so with the blocking case, we only give information up when information is valid. So now if you have image and information around that image, you get that, and you don't have to worry about handling the none case. So that's the improvement we've made in the OAK API. So it's no longer blocking. The next thing is, it came up on Discord, and we had an issue that a user was experiencing. And so a lot of times when we looked at cameras were hardwired into the board. So either a USB cable, a CSI cable, or even Ethernet, right, for it. So On some of the streaming cameras, we noticed that that people were having trouble when we lost connectivity on restarting. So Eric's gone in and improved and built up to make a more robust system on restarts and so forth. So hopefully that will help our IP camera streaming people. We've also developed a new service that one of our customers has used in the autonomous boat area. But what we can do for you is we can convert your models now. So if you model train and you come out with either a YOLO or a MobileNet SSD or so forth, or you impose estimation, what we can do is we can, if you contact our sales people on your platform, what we can provide for you in a service is to convert those over to Tensor RT, which is an optimal format to use in the Jetson platform. And also, if your Jetson platform does it on the YOLO case, we can actually get it down to precision int8, and that causes a much better execution time without loss of accuracy in it. So we can do those. Again, those are for our platform customers. So if you're interested in those, just contact our sales team on it. So that's what we have in 1.30. Like I said, we're very excited. It's fairly straightforward to update. The desktop will automatically show you at the top that you need to update. Just click on that and it will install all the benefits that we're talking about today. So with that, I think we're ready to move into Kalman trackers, and here comes the interesting part you're all waiting for. So, Steve?
Cool. Thanks, Steve. And Liz as well. So yeah, let's dive into the Kalman tracking. I'm assuming that some of you are familiar with tracking in general and what tracking tries to accomplish. You may have used the Centroid tracker or the covariance tracker, I believe it is. There's two trackers that we have in there.
Yeah. That's all right.
Anyway, yeah. So Kalman tracking is pretty tangential to Centroid tracking. It just adds a few layers on top of that, which allow it to gain a little bit of robustness. So for those that are unfamiliar with Kalman filters in general, it's a really popular signal processing algorithm. You see it in a ton of things, LiDAR, stuff like that. Anytime that you're trying to smooth out noise from measurements, that's another application of it. But in tracking, what we're really utilizing is the ability for the Kalman tracker to make a prediction one step into the future based on what it's seen in the past. So what you have at the bottom of this slide here is kind of a visualization of that. Let's say that your present frame is here at K, and then you've got all your previous frames. What you're looking at is a hollow circle, which represents the prediction made by the Kalman filter, and then the measured point, which is the solid circle. And what you'll notice is that in the future, you can actually project what your predicted point would be without actually having seen the measured point. So that comes into play later on in your tracking, and we'll talk about why that is in the next few slides. So let's go to the next slide, please, Liz. So what we've got here is a breakdown of how the Centroid tracker works. So with the Centroid tracker, you're not actually using predictions at all. What you're looking at with the Centroid tracker when you're trying to associate the object from one frame to an object in another frame is just the distance. You're just saying which object is closest to the object that I last saw. And then you're assuming that those two objects are the same thing. So I guess a refresher on tracking for those of you that might be a little bit rusty on it is basically what you're trying to do is you have all these objects coming in from your inferencing, and you can't really tell what object is which from frame to frame, right? So what you're really trying to do with any kind of tracking, be it Centroid or Kalman or any of the other types of tracking out there, is you're trying to basically chain together these objects and say, this is the object that I saw from frame one all the way to frame whatever you're at, and just keep track of which objects which. So for the Centroid tracker, you're just looking at the measured point from the previous frame to the measured point from the frame that you're actually in. So what you might notice is that the hollow point in every one of these frames is simply the point that you saw from the last frame. And then it's going to compare the distance and make the association based on whichever distance is minimum. And here we're looking at a single object, but you can probably extrapolate how this would work to multiple objects. Basically, would just take the nearest object from the previous frame and then assume that it's the same object in the other frame as it goes through. So next slide, please. So Kalman tracking, on the other hand, will use the predicted points from the previous frame instead of the points that it actually saw measured. What this allows you to do is, since the Kalman tracker can kind of converge on the motion of the object and understand how it's moving and really make accurate predictions based on where it's going to be one step ahead, you'll get much tighter clusters. So you'll end up with your predicted points being really close to the points that you're actually seeing in each frame. What it also does is it considers the inertia of the object. So that gives you kind of a robustness in terms of, okay, this object is going to be here and this is the way that it's moving. So it kind of prevents some certain hiccups in terms of when you might have two objects that are really close but moving in a different direction. And that it's a little bit more computationally expensive, but it's not something you'll likely notice. But it does give you that extra bit of robustness that you're going to need if you're looking at some more difficult situations of tracking. So next slide, please. All right, here's just a side-by-side comparison of a couple scenarios that you might run into with a centroid tracker versus a Kalman tracker and how they'll both handle each. So for the centroid tracker, recall, all you're doing is looking at which points are closest from the previous frame. So if you've got a scenario like this where you've got two objects walking side by side, assuming they have legs, you can kind of see here in the fourth box, if these objects get a little bit mixed up in a frame, it's going to make the association incorrectly. It's going to say, well, okay, my green object is closest to what I'm seeing with the blue object and vice versa with the green object. And it's going to assume that those two are, it's going to match them incorrectly, basically. And that incorrect match is going to carry on through your tracking. So anytime you have a switch like that, it could throw off your results and it could skew things a little bit. But the Kalman tracker, however, since it uses the predicted points and it's not actually worrying about the points that you're seeing, you're going to get a much tighter cluster, and the distances that it's actually computing in order to make the associations are going to be much smaller and more representative of how that object's actually moving along. And we have another scenario on the next slide. So, this is actually should be scenario B, but yeah, two objects that are crossing paths is what we're looking at here. So centroid tracker, if you look at these objects, you can kind of tell what I was trying to show, which is that they're moving from the top left and the top and the bottom right of the screen to the opposite parts of the screen. And these are just frames that you might be capturing from your object detection. So at some point when they cross paths, you're going to end up with 2 points that are very close together. And it's got the potential to make that same kind of mistake from before if you're working with the centroid tracker, which is these points are really close to these objects that I'm actually seeing. So it might mix up the actual objects and then make a switch without regarding the actual inertia of the objects. But on the bottom, you can see how the Kalman tracker would handle it, which is while these points are close together, you not only get the effect of your predictions being closer to where the actual objects are going to be in reality at that point in time, but you've also got the inertia consideration. So if you end up with a situation where you've got 2 points that are really close together and it's kind of a toss-up as to which point belongs to which object, the Kalman filter is going to be able to track, to consider the inertia of that object and say, well, the motion that I'm seeing from this object isn't capable of such erratic movement where it can just switch directions in a split second. So in the event that you have a toss-up, it's going to consider those motions and kind of weigh those along with the actual points that it's seeing. And that gives you a little element of robustness against situations like that. I think that might be the last slide I have in terms
Hey, Steve, we have a quick question here from.
Yeah, sure. No, all good. Good time for it.
Yeah. And his question is, do you think a Kalman tracker is effective to tracking people, the motion in the crowd when they move rather chaotically?
Yeah, totally. But a crowd is, so the tracker will be able to kind of eventually converge and understand. There's a tracker for each object first. Let me just preface with that. And what the tracker does is eventually understand what each object is capable of and how the motion of that object behaves. So it's going to be able to kind of, I guess, give an element of trust to how that object is capable of moving erratically and things like that. If you've got people running around and they're all in a crowd, going to be honest, it's going to be tough to track those people no matter what you're working with. But if you have people that are relatively sparse, like, I mean, maybe a medium density crowd or something like that, and if you have motion, like if they're not just like doing sprints back and forth, then you should be fine with the Kalman tracker. It really depends on the situation. It'll be able to handle it better than something that's a little bit more naive. But whether or not it'll be perfect is really dependent on your first of all your detections, and also just the computational power that you have. So I would say it's the best that you can get so far.
Yeah. Then I think people, so like AB is asking, how does it do that? Is there a library? And so the question is, yeah, we've built it into our APIs now. AB, I don't know, Steve, you're going to do a demo, right? Or of it with
Yeah, a
some
quick
videos.
demo.
So we'll see the application on it. And then, anything on Kalman tracking, it really depends, on FPS speed, things like that. It all depends on the hardware. That was the other question on it. So
yeah. And
hardware
if you're
focus.
interested in like the internals of the Kalman tracker, or Kalman filter rather, and the actual algorithm itself, there's some good literature out there. If you ping me on Discord, I can get back to you with that. So, but that's a little bit out of the scope of Hacky Hour. That's more, academic stuff. So yeah, if I could share my screen real quick, I've got some pre-recorded videos. I would show them live. However, I've noticed that if I'm sharing, where is it? If I'm sharing my screen, my computer, I don't think this will work, but let's try. How's that? You guys see it?
No, not yet.
Oh, I see. Okay. Well, it says host disabled participant screen sharing.
Oh, okay.
We can see you, but not your PC.
Yeah, I'm not the important one here. Yeah, but
Okay, there you go. That should work now.
Oh, perfect. Okay. So the code is here, by the way. It's not a really tough URL to follow, but if you go to our GitHub and you search Kalman Hacky Hour, you'll be able to see it all here. The reason I'm not showing it live is because when I share my screen like this, it chews up a lot of my CPU, and then I get really like the time between frames suffers, and that's really important for tracking. So I'll just kind of go ahead and show you some recordings that I have about the videos that we're looking at. So here's an easy video, right? And this might not look easy, but it actually is. You've got some really solid detections. It's not really that difficult for the actual object detector to do its job. And this kind of the scale of the objects are kind of similar. So I'll show you what I mean by that with the next video.
Steve, we're not able to see your screen.
Yeah, so it's Steve on Steve right now.
Oh, for real?
We don't see Steve and screen.
Okay, hold on a minute.
Steve B, yeah.
Let me try this.
There we go. Now we
is
can
that better?
See it. Yep, that's better.
Awesome. All right. Yeah. So what I was saying is that this video here is our easy video. You've got people walking in more or less a straight line. There's not a lot of different scales of the people. They're kind of all the same size. And that's really helpful. You've also got some really good bounding box detections, which is kind of the crux of all tracking, is that you want your object detector to be able to perform as perfectly as possible. If you have a poor object detector and your detections aren't coming up, tracking is just going to fall apart. So that's something to keep in mind, is that if you want accurate tracking, you need an accurate object detector as the baseline to make its tracking predictions off of. But here's the difficult video. And the reason this one's difficult is that you've got some occlusion here with this pole as people walk by it, same with the light. And then you've got some really different object scales. Like at the back of the video, you've got people that are really small. And then as you get to the foreground, the people are really large. And the reason that that makes things difficult is A, obviously the tracking, but B, you also need to consider the fact that when you're doing these trackings, you set a pixel threshold, right? As to what kind of associations you can make and what the boundaries are for those associations. So when you say, okay, I'm going to give that pixel threshold as 100 or something like that, 100 pixels in the foreground is not the same as 100 pixels in the background when you're dealing with bounding boxes that are different sizes. So it basically what it's going to try to do is say, if I've got two people that are 100 pixels away from each other or beyond that, then I'm going to consider those a new association. Now, 100 people could be like easily 100 pixels away from each other in the foreground, but then when you get into the background, you can fit more people in 100 pixels, I guess is what I'm saying. And that kind of throws things off. Really, it's to boil it all down, it's just different scales are tricky. But anyway, let's actually look at the tracking here. So what I've done is added a function that will keep the bounding boxes colored based on the object being tracked. So here's the centroid tracker in this scenario, and it's pretty simple. So it's doing a good job. In a case like this, I would probably opt for the centroid tracker because it's a lot quicker and it's just easier to conceptualize and manage and stuff like that.
So Mr. Euclid beats out Mr. Newton in this case. Right?
Occasionally, yes. But the Kalman tracker, let's look at how this does. You won't be able to notice any slowdowns, which is good. But I mean, it is rather quite a bit slower than the centroid tracker. But anyway, here's the Kalman tracker. So what you've got, it handles these situations a little bit better when you've got people up here and they're all, crossing paths and they're all small and stuff like that, and they're tricky to handle. But again, that was an easy video. So let's take a look at a hard video. So here's the centroid tracker in the difficult scenario. So you can see here that, yeah, it loses a lot of bounding boxes. And the reason for that is the threshold, right? So kind of what I said earlier, you've got a threshold of say 40 pixels. These people, as each bounding box from each frame is more than 40 pixels, it'll assume that it's a new detection and therefore a new person. Whereas up here, 40 pixels is just fine to match a person to another person because the next bounding box is always within 40 pixels of the last bounding box. Another thing is that the Kalman tracker will make the predictions, right? So you're not actually worrying about the point that you saw the bounding box in at the last frame. You've got predictions coming at each frame, so you're usually going to be a lot tighter in terms of where these things are showing up and where each detection is showing up for the comparison's sake. And let's take a look at how that works. So for this, you'll notice that first of all, when this person passes through this this pole, you'll notice that it picks it back up, and that's because when you lose a bounding box, you still get the effect of the Kalman tracker predicting where the next bounding box is going to be. So when it sees that bounding box again, it's got a point that's a lot closer to where it actually appears versus just using the last point that it saw. And you'll notice there's a lot less of the clutter in terms of the mispredictions when you've got people moving like this. Now, you'll see that it isn't perfect still, right? There's still some hiccups here, and these guys just start running out of nowhere, so that's tough, and it loses that. But yeah, this is hopefully a good demonstration of not only the limitations but also where you can benefit from that. And I didn't do a whole lot of tweaking in terms of the thresholds. If I were actually using this in a production environment, I would kind of experiment with thresholds and see which one works best. And another consideration is when you've got a video like that and you've got a lot of different like scales in terms of what your objects are that you're trying to track, I would consider just setting up a region of interest as like the foreground or the background, and then only considering that part. So for that video, let me show you what I mean. If I were to say, let's see here. If I were to say, okay, I'm only going to use like the lower 2/3 of this video because up here, there's a lot of clutter. There's a lot of stuff going on that doesn't really make a whole lot of sense. So I'm just going to keep the video as like where, I don't know if you can see my mouse, but where I'm drawing it down, like maybe see where the graph starts. If I were to say from there down is the only thing that I'm going to consider, that would allow me to get a little bit more, I guess, give a little bit more leeway into the thresholds, because I'm using objects that are always going to be of similar scale. So I don't have to worry about trying to strike a happy medium between, okay, this works well for the background and this works well for the foreground. I'm only considering the foreground. So I just deal with what works well for the foreground. And that about sums up what I've got for you guys. So I hope that was informative, and I will pass it over to Tyga now if I can figure
Yeah,
it
so
out.
quickly, Steve, on some of the things to get back to processing power, which is, we know in the Centroid, even if you ran it on a Raspberry Pi, it would struggle, right? So maybe not heavily, but probably this should be something where you at least have an Nano, but recommended Xavier if you're going to put it out into the field. Probably.
Yeah, totally. I would for sure be thinking about an Xavier, and this isn't something that is like, I maybe talked it up a little bit too much in terms of how heavyweight it is. It's really not that heavyweight, but definitely if I were to be using this and I were to be tracking a lot of different objects and stuff, I would reach for the Xavier over something a little bit less capable every time. So that's also something to consider.
And really what I'm talking about there is more around the ARM core. So if you had just an regular ARM processor or ARM chip with lots of cores, it would go that way too, because it won't use the GPU, will it, in the detection process, or does it?
No, I don't think it does.
So it's really about throwing a bunch of CPU computations at it. So and so forth. Okay, thanks. Sorry.
Yeah, no, thank you guys. I stopped sharing my screen, right? We're all good?
Yeah, you did.
Okay, cool.
Okay, so you should see my screen again. And next we're going to introduce Tyga Ashita, who's going to be covering AprilTags. Tyga?
Cool. All right. Thank you, Liz. And great demo, Steve. Thanks for everyone joining in. So yeah, I'm going to be going over AprilTags, what they are, how to use it with HiQ. So what is an AprilTag? Now, AprilTag is a type of a fiducial marker. I like to say visual marker, but yeah, so it's a fiducial marker used in computer vision. So actually, before I go into the computer vision bit, take a look at this picture at the bottom, right? So this, in this scene here, this coin is acting as a fiducial marker here in this scene. I mean, to our brains, right? So without this coin, it might be hard to infer the size of the Raspberry Pi and a neural compute stick. But if we add in this object that we're really familiar with, it kind of puts a sense of, kind of adds a basis of comparison there, and to make it really easy to infer the size of the other objects in the scene. And so, now the AprilTags, that's also, it can be used for a point of reference or a measure, right? The software is able to precisely locate the pixel location, the orientation, and the identity of the tags. So this robustness makes AprilTags suitable for wide range of applications such as augmented reality. In augmented reality, you'll probably use the size of the AprilTag to kind of overlay the synthetic image into your camera frame with a correct scale and stuff. And there's many more use cases there, but you probably most of the time they're using the scale of the AprilTags to correctly overlay the synthetic image, right? And then as Steve mentioned early on, it's heavily used in robotics, and that's because with the AprilTags and it's able to give you their location and identity and orientation. People use that to implement SLAM, so localization and mapping. Really cool stuff there. And it's also used for camera calibrations as well in some systems. So yeah, conceptually, AprilTags are similar to other 2D barcodes, such as QR codes, AR tags, and I think there's C tags and stuff like that, and those all differ in its intended payloads, right? AprilTags were designed to be low latency, so they're very lightweight, but then at the same time they're also pretty come with high accuracy. So, good detection rates, and, they're able to do that because, they're not cramming a lot of data into these tags, right? So, most April tags, they, depending on the tag family, they range between 4 to 12 bits of data. So that's, 4 bits being like around 16 unique IDs, and 12 bits being around 4,096 unique IDs. So yeah, and those all differ with the different tag families. And right here, this picture to the left are showing some of the different tag families here. So that's tag 36H11. That's a pretty common one to be used. These other ones are not standard, and currently we don't have support for these other ones here. We support like all the standard ones, which is tag 36H11, tag 16H5, those type of April tag families. And so by name, you could kind of, it kind of gives you some information here. So this tag 36H11, the 36 stands for, it means that there's 36 blocks, or block bits is what they're calling it, in this image. And then this H11 is the minimal Hamming distance, right? So the cool thing about these is it comes with bit correction, so it can detect the errors in the bits that the camera receives through the software. And that kind of also adds to the robustness and makes it work really well in different lighting conditions and different viewing angles. Yeah, so that's the name of tag family, what it describes of the tag. So yeah, so there's all these different tag families, and if you're wondering like which tag family to use, it's kind of trade-offs, right? With anything with engineering, it's higher bit representations. Higher bit representations are more robust, because there's more data there. This higher minimal Hamming distance can correct more of the bits that it detects as errors. But generally they're harder to detect, right? The camera really has to detect all 36 bits, for it to correctly identify the tag. So if you want something that works more for long distances, you probably want to use like a smaller tag family, like say tag 16H5. And the reason why those work for better in longer distances is because those larger block sizes really make it easier. It makes it more easy to detect by the algorithm. But then, with that, it comes with more false positive detections, right? So these larger blocks, so now you might have, say your TV screen might look like an April tag. So it's just about the trade-offs there and choosing different tag families. And also camera resolution as well. So if you're using like a lower resolution camera, you're gonna want to use like a smaller tag family. Those the bigger blocks are better picked up by the camera image and stuff like that. And lastly, it's like the distance as well in the scene. So these detections, they're really good at close ranges, but they start to fall off in longer distances. So in my testing, it works pretty good, and I'll show it in the demo, but I'm seeing around like a 2-meter range, right? And then the detections get pretty poor past that. And so, yeah, that's all things to consider when choosing a tag family and stuff. And so you're probably wondering how it works. And so this part is not unique to April tags, and most fiducial systems like visual system work like this. Like the first step, it's a unique feature detection. In the case of the April tag, it's looking for the square here, right? And so to help that, when you're printing April tags, you're gonna always want to have this white border here, this 1-bit block width of the border around here. That's what it's looking for first, right? So it does a unique feature detection. Once it detects the square here, it goes in to decode the inside of the marker, which they call the marker interior, and that is the payload. So that gives you, the unique identifier and also the orientation of the tag and stuff like that. So when you're printing these out, you want to really make sure that it's on a flat surface. So I've seen people use foam boards for this. Some more production solutions might be to print it on like thin aluminum sheets because those hold up better outdoors and stuff. So yeah, that's kind of all the stuff about April tags. So let's go into our alwaysAI docs to kind of look at the APIs here. So let me go share my
Hey,
screen.
Tyga, while you're
Yeah.
setting that up, we have a question if you don't mind.
Yeah.
They're asking, what is it similar to Aruco markers? What is the difference if not? And Steve's actually answered it, but I just thought it'd be good to bring it up live and see if you have anything else you guys wanted to add. Steve said they're very similar, and he provided everyone a link. If you guys want to go to, I can put this link in the chat, but I don't know, Tyg, if you had anything else you wanted to add while you're setting things up.
Yeah. So they're all, they all fall under the category of a 2D barcode. But it's just, some contain more tuning parameters for it to work, all that stuff. So that's also something that you're going to want to gauge, but they're all pretty similar. With QR codes, they hold more data. So you're, probably seeing those a lot at restaurants and stuff like that. But those QR codes aren't really meant for long range detection. So you're not going to be able to scan a QR code from more than a couple inches away. But Aruco is pretty similar to April tags in that they're just, they provide unique ID, the orientation. So yeah, they're all pretty similar. Yeah, they all.
Yeah, it's great.
Cool. So yeah, so this is the starter application that I'm going to be demoing today. It's under the alwaysAI repository on GitHub. It's called the April tag detector. Some useful links here. So this is what I'm using for the demo, but pre-generated tags can be downloaded here. These are the different tag families here. So those can be printed and used for testing. But if you want your own April tags, you can also use this repo here to generate those. These are all from April Robotics. These are the people that made the April tag. And so it's cool that they, provide these resources for us to, make our own April tags and stuff. So the setup, the usage, they're pretty similar to all of the rest of our alwaysAI applications. So I will not go with those. Let's just go into the documentation. Cool. So the first class you see here is the April tag detector. And that is the main class that you're going to use to detect April tags and kind of see a typical usage here. If you're familiar with our platform, you already know how to use this. It's pretty simple. What you first do is instantiate the detector. It has one parameter here, that's the April tag family. These are the families that we support. We support tag 16H5, 25H9, 36H10, and 36H11. So that's the parameter there. Once you instantiate it, you just call this detect function on it, which takes in an image and returns you a list of April tag detections. And this is what that looks like. It has these couple properties here that we're interested in, the tag ID. So that's the actual payload or the unique ID that the tag was created upon. And also the corners. So the top left, top right, bottom left, bottom right corners of the detection. And we will see those here. So we could take a look at the code. I'll just go over it really quickly. I kind of already went over it, but this is the starter app detector here. A typical pattern here to start up a webcam as well as a video stream. Pretty so. This markup image, if you want to show the tag IDs, you just set this to true. Sometimes you might not need that. This is just all for visualizations here. So you can mark it up on the frame to see all the April tags it's detected. Then I'm sending that data to the streamer and, our standard Edge IQ patterns here. So let's take a look here. I have it already running. So these are the tags. Let me go over into my weatherman mode here. Cool. So these are the tags. Kind of put them in different orientations to show you that, they contain fixed orientation. So maybe this isn't the best way to show it. You would probably want to hang these with the corners top left corner where the ID is, like upright. But yeah, so you can see all of this here. And, these orientations come into big play in robotics and stuff like that. You can kind of use this data to see the orientation of your robot. And that's kind of what they do to do the SLAM stuff. So it's pretty cool here. So this bottom left one here, I kind of talked about the stages of a AprilTag detection. The first stage being the unique feature detection. So it detects the square and then it decodes the internals to get the tag ID and the corners and stuff like that. So, like it's really, like I mentioned, it's really important to print these with this white border around here. Right now it's still being picked up because the background is pretty white, but kind of have this sticky note here. So if we put the sticky note here, all right, that should start to fill. There. Put one at the bottom here. It's not working with me. Cool. Yeah, so you can see I, kind of eliminated like the software for being able to pick up the AprilTag. So it's failing on that first stage here. And so, yeah, it's pretty important to leave that white border around. It's, in the case of an AprilTag, that's what it's using to detect the AprilTag. And then, that once it detects the AprilTag, it decodes the tag there. So, yeah, some of the, pitfalls, I guess, with AprilTag, like I mentioned, is distance. Let me, if I can get my AprilTag here. So I'm gonna use this AprilTag I have on my phone here to kind of show you guys what I mean by the distance. Let me flip that over here. So yeah, so at the close ranges is pretty good here. But you can see as I start to slowly go backwards, it's going to start failing. It's actually doing pretty good still.
The video might be stuck for me.
Yeah, it is for me too.
Yeah, we've got you putting pink stuff up on the screen. So
Maybe we could just reshare. Maybe like Zoom just got stuck for a second.
Okay, yeah. Stop share. And then let me share that again. But is that,
Let's see.
you guys able to see that?
It says that you've started your screen share.
Maybe I think my system is kind of just being overloaded. Let me go ahead and kill
Zoom
some of
tends
these
to put a lot of strain.
Yeah, let me kind of close out these applications here.
Let's see, we do have another question.
Yeah.
Is this marker usage more effective than usage of bare Arabic figures like 1, 4, 56, and so on? So I think that means like just using maybe like regular numbers and letters and trying to parse those. If Andrew, if I didn't read that correctly, if you want to type an extra clarification or even raise your hand, you can feel free to do that too.
Yeah, I mean, I think this question is talking about using AprilTags versus like other methods like OCR. And it kind of just goes kind of your intended use case, right? Like, the thing with AprilTags is you have to kind of set your scene up. So that's like really important. And, with OCR, I guess if you're going to stick these on the wall, they'll be the same type of thing. But the OCR doesn't give you is, like I mentioned, the precise corners and the orientation of the tag, which then can be used to kind of feed back into your system to detect the robot's orientation or the camera's orientation, right? So it just kind of depends on what you need out of the detections.
Nice. And now I see your screen, so it's perfect.
Okay. Cool. Okay. So yeah, I'm just gonna show like kind of like the range stuff here. So, like close by, it's doing pretty good. But as I slowly start to go back here, we can kind of see it still does pretty good. I'm probably about 1.5 meters away. still picking it up, but as I get further and further, kind of drops those detections. And so that's one thing to keep in mind is like that's another thing is like the distance from the tags. There's like other fiducial systems that use, natural landmark features as well. So it's, kind of just weighing out the environment, stuff like that. Outdoors, maybe the April tag is not the best option, but I've seen cool stuff where there's this repository actually on GitHub called Tag Slam that kind of showcases using April tags and a drone going through a tunnel and doing real-time slam. So I guess April tag is just heavily dependent on your environment and stuff like that. But what it can do, it's really robust in what it does really well. So I'll show the other pitfall. It's just kind of like the conditions here. So when it's, fully illuminated, it's pretty good. I can't dim my house down, but I could dim the screen. So, even at these low brightness levels, it does really well. But, maybe April tags shouldn't be used in the nighttime and stuff like that. So you can see as it gets dimmer, it's starting to, actually, it's doing pretty good actually here. There you go. Now it's not detecting anymore. So that's also another thing you want to keep in mind. It's just the illumination that these tags have in the field. So probably not good for, nighttime applications and stuff like that. I'll show these tags one more time again. Probably write these tag IDs down. They might be coming in play, sometimes they might get you a swag box or something. So yes, and that's my demo. I'll turn it back over to Liz.
Great. Thanks, Taiga. That was awesome. I love that. I love seeing that. Okay, so do we have any final questions before we close out this wonderful Hacky Hour today? Yes, and we see here, this will be available to rewatch on YouTube at a later time if anyone would like to. And Lila has provided all of the links to GitHub, links to alwaysAI.co, and other links to our Discord channel in the chat if needed. Oh, let's see here, we got another question. Right, so those links are being provided again in the chat if you need them. All right, so if there are not any other questions, without further ado, thank you all for sticking around to the very end. Now let's get right to it and ask our final question to see who can win our swag box. So this swag box contains a premium cotton alwaysAI t-shirt and an alwaysAI hat, which Steve Grisette was modeling so nicely earlier. And then you'll also get an alwaysAI sticker to go along with it. So the question is, and we'll ask the question and then ask each of the attendees to put their answer in the chat window and make sure that it says to all panelists and attendees, so that it goes to everybody and it'll have a timestamp on it. So just drop your answer in there. So the question is, what was the tag ID, the April tag ID that Taiga flashed on his phone during his demo?
Okay, nice. We do have an answer. It looks like from my chat, AB got his in first. That's that's another one. I wrote down 2, which is the one from his phone, but there were a lot on the screen. Yeah.
No, it should be 2. I just flipped through it. I have all the April
tags. You have all of them saved on your phone. Yeah.
All right.
And Andrew also got the right one, but AB was just a little bit quicker.
Yeah. AB, all right. Congratulations. You are the winner. So we will, if you can send your address, your mailing address or PO box to Lila.
Yes.
And I know you have,
Yes, we already, yeah. In the future, we're going to make sure that, you know, if you log into Zoom on your Zoom name, that you send it to us privately here. AB has done that in the past, so we're aware of, you know, his email and stuff. But yeah, thanks everyone for playing.
Thanks everyone so much for participating in today's Hacky Hour. And again, as soon as we have new product releases or new exciting features to share, we'll be sure to be hosting another one. But you know, feel free to let us know any content that you might be interested in having in future Hacky Hours. In fact, we have a small poll that we'd love to run quickly and ask you, what kind of content would you like to see in future Hacky Hours? So if you don't mind taking a moment to answer that poll and let us know what you want to see more of. We'll be sure to incorporate that into our future Hacky Hours. Yeah, model training looks like it's a very popular topic. It's great. All right. Well, thank you again, everyone. I appreciate you filling out the poll, and we'll make sure to incorporate some of this content in future Hacky Hours. Please, again, feel free to view this recording on YouTube along with our other past Hacky Hours, and feel free to follow us on our Discord channel and our other social networks as well. Thanks, guys. Have a great day.
Thanks, everyone.
Thanks, everyone.
Thanks, guys.